In this video, we will solve an exam task on moist air given in January 2023 in the course Mass Transfer in Environmental Engineering. The task is as follows. The illustration below depicts an equipment used to produce a ventilation flow G6 for a climate-controlled storage. For an outdoor climate, according to G1 in the illustration, A. Draw the system in a Mole diagram. B. To what temperature does the heater need to heat? C. What is the power used in the cooler and the heater respectively? D. What can the reason be behind the placement of the heater, that is, before rather than after the mixer? On future exams, I will include the following instruction. Solving balances by measuring distances in millimeter along a mixing line is not taught in this course and is not counted as a valid solving method on an exam in this course. Okay, let's start solving the task. The state of flow G1 is given in the task as wet temperature of 39 degrees and relative humidity of 60%, so we can mark G1 in the Mole diagram. Since the splitter does not change the state, G2 and G3 have the same state as G1. The state of G6 is also given and has a temperature of 20 degrees centigrade and a relative humidity of 50%. As 5 degrees centigrade is way below the dew point for G3, we know that the relative humidity goes to 100% in the cooler. Thus, we identify the state of G4 in the Mole diagram and the path the air takes to get there. First down to the 100% relative humidity line, that is the dew point, and then it follows the 100% line all the way down to 5 degrees centigrade. We know that G6 is formed by mixing G5 with G2, so thus G5 must be on the same straight mixing line as G6 and G2. We also know that G5 is created by heating G4, and thus X5 equals X4, so the same water content. The state of G5 can thus be found by the intersection of the mixing line and the line for constant water content X4. We can see in the graph that G5 needed to be heated to around 18.5 degrees centigrade, which is our answer to question B. Before we continue with our calculations, let us interpret the graph and make a prediction of the flows. The water content X6 is way closer to X5 than it is to X2. Thus, most of the mixed air G6 is due to the air G5, and G5 is thus much greater than G2. While we are interpreting the diagram, let us also answer the theory question D. If the heater was placed after the mixer, the mixing line would go below the 100% relative humidity line. We typically never want that to happen in a mixer, although the cooler used here must be designed to allow for condensation. There are two reasons we do not want condensation in the mixer. Firstly, it may cause corrosion, and secondly, it may produce results that are difficult to predict. In our case, it will be very difficult to create a mixture that has the same water content as G6, since that part of the mixing line has a relative humidity above 100%. To answer question C, we first need to calculate the flows. To do that, we write down mass balances, or more specifically, component balances for water and for air. First, however, let us translate the volumetric flow to a mass flow. At 20 degrees centigrade and a relative humidity of 50%, we have a dry density of 1.19 kg per cubic meter. So thus our flow is 1 cubic meter per second multiplied with 1.19 kg per cubic meter, which gives us 1.19 kg per second. Let us write the balances for the mixer. For air, we get in equals out, that is G5 plus G2 equals G6, which we can write as G2 equals G6 minus G5. For water, we get G5 times X5 plus G2 times X2 equals G6 times X6. Let's get rid of G2 and write G5 times X5 plus G6 minus G5 times x2 equals G6 times x6. Collecting G6 on one side, we get G5 times x5 minus x2 equals G6 times x6 minus x2. And we can calculate G5 as G5 equals G6 times x6 minus x2 divided by x5 minus x2. With our values from the Mollier diagram, we get that G5 equals 1.19 times 0.0072 minus 0.0421 divided with 0.0054 minus 0.0421, and we get 1.13 kilogram of dry air per second. And we get G2 equals G6 minus G5, so 1.19 minus 1.13, so approximately 0.06 kilogram per second. Note that our prediction that G5 is much larger than G2 was correct. Our calculation thus seems reasonable. Reading the enthalpies H3, H4 and H5, we get approximately 156, 19 and 32. An energy balance in equals out for the cooler becomes G3 times H3 equals G4 times H4 plus Q cool, which since G3 equals G4 equals G5 gives us Q cool equals 1.13 times 156 minus 19, or 155 with the unit kilogram per second multiplied with kilojoule per kilogram, so that is kilowatts. An energy balance for the heater gives us G4 times H4 plus Q heat equals G5 times H5, and Q heat is then 1.13 times 32 minus 19, or 15 kilowatts. So, to summarize, the heater needs to heat to 18.5 degrees centigrade, 155 kilowatt is removed in the cooler, and 15 kilowatts is added in the heater.